Hello everyone, in this video we will introduce an important technique for designing control algorithms. We will explain how to combine a pole placement method with an integral control action to eliminate steady state errors. Before I start, I would like to mention a few important things. First of all, compared to most of video tutorials on control, estimation, coding, and machine learning that are available online and on YouTube, I decided to go the extra mile. So, besides this video tutorial, I created the post that you can see over here that nicely summarizes everything that I will explain in this video. This post contains equations, derivations, graphs, and even MATLAB codes. It took me a significant amount of time to design and create this post and the lecture. Since I do this in order to teach others, more or less for free, how to design control algorithms and control theory, please consider to support my channel by pressing the subscribe and like buttons. Thank you very much. A link to this post is given in the description below this video. Apart from this video lecture and this tutorial, I created a number of videos and tutorials that address different engineering, machine learning, and control engineering topics and different approaches. For example, if you click over here, you can find the control systems tutorials I created. I think there are more than 20 tutorials over here. Also, I have here OpenCV tutorials I created, or here you can find machine learning tutorials. Let us start by explaining the main motivation for creating this tutorial. When designing control algorithms, we are primarily concerned with two design challenges. First of all, we have to make sure that our control algorithm behaves well during the transient response. That is, as designers, we specify the acceptable behavior of the closed-loop system during the transient response. We will illustrate these design specifications by considering the following example. So let us assume that we have a control system and that we want to design a closed-loop controller. Now, let us assume that the system produces a hypothetical response, a closed-loop step response that looks like this. The system's rise time is a very important design specification, and usually we want to ensure that the rise time is below a certain value. Rise time is usually defined as the time required for the waveform or the step response of the system to go from 10% of the final value to 90% of the final value. So let us apply this definition over here. So this is the 10% of the final value, this is the final value, this is 10%, 90% of the final value is, for example, over here. So our rise time is basically this interval, TR. We want to make sure that the system's rise time is below a certain value. For example, 0.1 second. Another important specification is the percent overshoot. Usually the percent overshoot is defined as the amount that the waveform overshoots the steady state or final value at the peak time, and this value is expressed as a percentage of the steady state value. So let us apply this definition. Here is our final value, and we draw a horizontal line. Then the next step is to identify the peak. The peak is over here, and next we draw a line that reaches this peak. So the overshoot is this value expressed as the percentage of the final steady state value. So if we divide this value by our steady state value and express the result as a percentage, we obtain the percentage overshoot. Usually we want to make sure that the percentage overshoot is below a certain value, because we don't want our transient response to be like this. Here the percentage overshoot is huge. Besides ensuring that the system closed-loop response meets the design specifications and desired behavior during the transient response, we also have to make sure that our system is able to accurately track set points or different reference point values. For example, let us say that we want our system to track a step function. And this is the desired system behavior. So somewhere in the steady state, the system has to approach this value. Obviously, this system doesn't meet this design specification since we have a steady state error over here, and this is not a desired behavior. We have to make sure that this steady state error over here is eliminated. So a desired response of the system would look somehow like this. And then asymptotically, we should approach our reference signal. In your introductory course on control systems, you have probably heard of a pole placement problem and the possible solutions. It is okay if you didn't hear about the pole placement problem and how to assign the poles of the system. You will learn these topics in this video. Now, the classical pole placement method is used to stabilize the system, or it's used for improving the transient response of the system. So, for example, if we have a linear system shown over here, we want to design a feedback control matrix, K, and notice here that we have a state feedback control matrix such that the poles of the closed loop system are placed at desired locations. These desired locations will automatically ensure that the system's transient response meets the desired specifications. However, the classical pole placement method does not ensure that basically our steady state error, the value over here, for certain value of the reference signal, is eliminated. And that's one of the main drawbacks of the pole placement method. So we need to augment and we need to improve the classical pole placement method by adding an extra layer, an extra control layer. And that extra control layer can be achieved by adding an integral control action. So to repeat this important observation once more, the classical pole placement method can ensure that our transient response meets a desired specification. However, in most cases, the classical pole placement method cannot eliminate the steady state error. To eliminate the steady state error, we need to augment the pole placement method and the control algorithm that's based on the pure state feedback by an integral control action. The purpose of an integral control action is actually to eliminate the steady state error. And in this video, I will teach you exactly that. I will teach you how to combine a pole placement method with the integral control action in order to meet both design specifications, the transient design specification and the steady state error design specification. Consider the following state space model. This is a linear time invariant system where x is the state, u is the input, and y is the output of the system. Here, for brevity, we are assuming that the input dimension is 1 and the output dimension is 1. Also, consequently, we are considering single input, single output systems. Now, the classical pole placement design finds the feedback control matrix K and the control law U is minus K times X such that the closed loop system, given by the equation 2, is stable and that the poles are placed at the desired locations. So basically, we are trying to find a feedback control matrix and this control law such that the closed loop system that is obtained by substituting Q over here and obtaining this equation and ensuring that this matrix over here is Hurwitz or that its eigenvalues are in the left half of the complex plane. That is, we are ensuring that the system is stable and that the poles are placed at desired locations. These desired poles are going to ensure that the transient response of the system meets the design specifications. As we have mentioned previously, the issue with this approach is that although we can place the poles at the desired locations, we do not have full control of steady state error. So we need to upgrade our control method. And this upgrade is performed by adding this equation. So what happens over here? R is the reference signal or just a set point value. For example, we want our system in steady state to reach the point 10 or reach the point 20 or reach the point 30, and this is basically, for example, a step function. And C times X is our output. So Y is equal C times X. And this is the output of the system. The output of the system is the variable that we usually observe or measure. And what do we do over here? We are basically defining a variable xi that is an integral of our error. So this is our tracking error. So you can basically write r minus cx and you can assign this value to a new variable e, and basically this is our tracking error. So basically this is an integral control action. However, we will see this integral control action as the state of the system, and that's novelty. Now, if we differentiate this equation, we obtain the equation number 4. Now, if we go further, and if we combine this equation with our original state space model, we obtain something like this. So this is our augmented system. And we can write this system compactly like this. And what did we achieve by doing this? This is our new state vector. So besides taking the original states, we have another state in the system, and that's our xi coming from the integral action of the system. Now, we can straightforwardly apply the pole placement method to this equation and to this system. Basically, we can now design a feedback control algorithm, a state feedback control algorithm, where the states are x and xi, and we can use the pole placement methods to assign the closed loop poles of this system to desired locations. And this will ensure that the transient response meets the design specification, and since we have an integral action in our system, the steady state error will be eliminated. So over here, you can actually see the structure of your controller. For example, if our original x is the position of the system and velocity of the system, for example, we are considering a system that comes from Newton's law, right? The model coming from the Newton's law. You can see basically that this equation over here, our control equation, resembles a PID controller, right? Because we have a position, we have the basically velocity, and then we have an integral of the error. However, you can expand all these terms and you can see that the structure resembles the PID controller. The structure becomes similar to PID controller, not exactly basically a PID controller, but similar, since we have basically an integral action. Now, if we go a step further, and if we substitute our controller, the controller given by the equation 8, in our augmented system, we can obtain the equation number 9, the last equation in the series of equations, and basically this controller will ensure that this matrix, the new closed loop system matrix, or A new, is asymptotically stable. That is, it's Hurwitz. Now, we have basically solved a big problem over here. Next, we present MATLAB codes for implementing this control approach. The following code lines define the system, compute the eigenvalues of the open loop system, perform basic diagnostics, and compute the open loop response. So let us explain these codes. First, we clear our workspace, pack the memory, and clear the command window. Then, we define our system. This is a second order system, and let us compute the open loop poles of such a system. Okay, so the system is stable, open loop stable, and we see two poles or two eigenvalues of our system matrix over here. So let us define the state space model, the open loop state space model, and let us compute the step response. Okay, so here is our step response. Let us increase the line thickness over here such that you can clearly see this line, and let's see what happens over here by adding a grid. Okay, so what do we observe over here? We observe that our system is not accurately tracking a step signal because we want the final value to approach 1, however it approaches 0.5. And this is the main point from the beginning of this video. At the beginning of this video, I mentioned that a stable system does not ensure that you will be able to track accurately a step signal. So we need to change the controller or the system itself. Now, let us define the augmented system for pole placement. So basically, what do? We are defining the system. Okay, so let's see what's happening over here. I'm defining my A matrix, the matrix given over here. I'm defining a new B matrix multiplying U. Here it is. And this is BR, this is the matrix multiplying the R. R is the reference signal that we want to track. Okay, now let us define the desired closed loop poles. So let's see what's happening over here. These are my desired closed loop poles, and I assign them to be 3 times poles of the open loop system. So what I'm doing here, I'm shifting my open loop poles more to the left in order to ensure that the transient response of the system is faster compared to the open loop system. And here, since I have an integrator, I need an additional pole, and I'm shifting this pole to be 10 times further from the imaginary axis compared to basically the pole that is further away from the imaginary axis. That is, I'm shifting the third pole 10 times further away from the pole of the open loop system that is further away from the imaginary axis. Now here I will simply compute the feedback control gain by using the command place, and you can type help place in order to read more about this function. So this is a MATLAB function that computes a steady state feedback matrix K such that the eigenvalues of A minus BK are those specified in the vector P. So vector P is here in our case, and our A is not an open loop matrix, it's an augmented system matrix, and BT is again a matrix multiplying U. Okay, so let's see how this works in practice. Here it is, and here's my K matrix. So the place function will give you the feedback control matrix or the state feedback control matrix. Now, we define the closed loop poles for simulations. And we define our closed loop system since we want to simulate our closed loop system. That is, we define this equation over here or this matrix over here. Now, let us check the placed poles. It's a good practice, and here are our placed poles, and let's compare them with basically the desired poles. I see very good result. I see that the error in placement is very small in the order of numerical precision. Next, I define closed loop matrix C. And finally, we define a closed loop state space model. Basically, we define this system. And let's compute the transfer function to see what's happening over here. So this is the closed loop system transfer function from the reference signal. Watch out, here now the reference signal is the input and the output stays the output. Again, the input is now the reference signal. And let us compute the step response from R, from this reference control signal, to our output of the system. Let's see what happens. Okay, here's the result. Let us increase the line width and put the grid. And we have solved a big problem. Now, our system is able to accurately track a step reference signal. We can see that the steady state error is eliminated. And furthermore, we can observe that the system response is faster. This is a direct consequence of the fact that we have shifted all the poles more to the left in the complex plane. And you can actually observe all these details by comparing, for example, the rise time here in the final, or actually this is an open loop step response of the system. We can see that the rise time is, for example, 4.5 seconds, and our closed loop system has a rise time below 2 seconds. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please subscribe and support my channel. Thank you very much and have a wonderful day.